While you're watching this video, pieces of continents are slowly breaking off from below and are pulled down into the oceanic mantle, a hot, mostly solid layer that moves slowly under the seafloor. As soon as these fragments reach the mantle, they can trigger volcanic eruptions in parts of the ocean where there are no volcanoes. Plus, when continents break apart, it happens not only at the surface, but also deep down. But more on that later. This process can continue for tens of millions of years. The new study shows that Earth's insides are even more dynamic than we thought. It also explains why many volcanic islands, including Christmas Island in the Northeast Indian Ocean, contain unusually high levels of certain chemical elements. The thing is, these elements are normally only found in continental crust. Well, scientists did suspect that these elements showed up because some powerful forces deep inside the Earth took old, recycled pieces of rock and mixed them into the mantle. This process works a bit like when you mix together ingredients for cake batter. But before, researchers believed those elements came from two main sources: sediment that sank into the mantle as oceanic plates got pushed down, or from mantle plumes. Those are columns of hot rock rising up from deep inside Earth. However, these explanations don't fit all observations. In some volcanic areas, there's almost no sign that the crust has been recycled. In other places, the mantle seems to cool and too close to the surface to be affected by the rising hot rock. Scientists used to wonder how this could happen. Now we know that some of the material in those regions comes from pieces of continents that sink deep into the mantle, and these pieces affect the volcanoes that form above. The new study also suggests a curious idea. Continents don't just break apart at the surface, they peel away from below too. And this can happen over much greater distances than scientists thought before. Researchers used simulations to figure out how continents and the mantle behaved when stretched by tectonic forces. Their work is built on earlier research showing that when continents split, deep, powerful forces inside our planet create a mantle wave. This wave moves along the base of the continent at depths of about 90 to 125 miles. The wave moves extremely slowly, about a millionth of the speed of a snail, and gradually strips material from the roots of the continents. These peeled-off fragments are then carried sideways, sometimes more than 620 miles, into the oceanic mantle. Once there, they can trigger volcanic eruptions in the ocean for tens of millions of years. The research also shows that the mantle continues to feel effects of continental breakup long after the continents themselves have separated. Even after a new ocean basin forms, the mantle keeps moving, reorganizing and transporting enriched material far from where it originally came. To make this conclusion, researchers studied geochemical data from different parts of the Earth, including the Indian Ocean Seamount Province. That's a chain of volcanic formations that appeared after the supercontinent Gondwana had broken apart over 100 million years ago. Their computer models and chemical tests showed that right after the supercontinent Gondwana broke apart, a lot of magma with unusual chemicals pushed up to the surface. Over millions of years, this chemical signature slowly faded as less material came up from under the continent. The most unexpected discovery is that this happened without any help from those deep, hot columns of rock scientists used to think were needed. Now, to get an even clearer picture, let's sneak a peek into our planet's insides. Earth is about 4.6 billion years old. It was born from a huge cloud of dust and gas that slowly cooled, shrank, and hardened into the planet we know today. As it cooled, heavy metals like iron and nickel sank to the center, and lighter, rocky materials floated upward. This created the Earth's layered structure, with each layer having its own unique properties. The crust is like Earth's skin. It's our planet's outermost layer, made of solid rock. It's broken into huge pieces called tectonic plates that slowly drift over time. There are two kinds of crust: oceanic crust, and continental crust. The oceanic crust is about 4 to 6 miles thick. It's covered with a thin layer of sediments like sand, clay, and shells. Below that are dense rocks like basalt, rich in magnesium. As for the continental crust, it's thicker than oceanic crust and is located under continents. It's made of lighter rocks than oceanic crust. Beneath the crust is the mantle. It makes up more than 75% of Earth's volume. The top of the mantle is pretty rigid, but deeper down it becomes soft and partially molten, which allows it to flow slowly. This flow is what moves the tectonic plates. At the center of the Earth lies the core. It's made mostly of iron and nickel and has two distinct layers, the outer core and the inner core. The outer core is a liquid layer of iron and nickel. It's insanely hot, up to 10,800 degrees Fahrenheit, as hot as the surface of the sun. The outer core also generates Earth's magnetic field, which protects us from harmful solar radiation. The inner core is solid because of the crushing pressure inside the planet. It's also made of iron and nickel. Now, the Earth's outer shell, called the lithosphere, is made up of the crust and the uppermost part of the mantle. It's broken into large pieces, called tectonic plates. There are a few super large plates and many smaller ones. 6 of the major plates are named after the continents they carry, like the North American, African, and Antarctic plates. But even those smaller plates play an important role. For example, the tiny Juan de Fuca plate is responsible for many of the volcanoes in the Pacific Northwest of the United States. The plates are moving like a jumble of old conveyor belts. They move very slowly, about 1 to 2 inches per year. But over millions of years, this movement shapes the face of our planet. Most earthquakes, volcanoes, and mountain building happen where plates meet, pull apart, or slide past each other. There are 3 main types of plate boundaries: convergent, when plates move toward each other; divergent, when plates move apart; and transform. That's when plates slide sideways past each other. When tectonic plates collide, the crust crumples and buckles, forming mountain ranges. About 55 million years ago, India crashed into Asia, slowly creating the Himalayas, the tallest mountains on Earth. The collision continues today, so the mountains are still rising. Mount Everest, the highest point on Earth, may even grow a tiny bit taller over time. At some convergent boundaries, an oceanic plate dives under a land plate in a process called subduction. The land above lifts up, forming mountains, and the sinking plate melts and triggers volcanic eruptions. This is how some mountains in the Andes of South America were formed. When 2 oceanic plates collide, one usually slides beneath the other, creating deep ocean trenches, like the Mariana Trench in the North Pacific, the deepest point on Earth. These collisions can also form underwater volcanoes that eventually rise above the ocean and turn into island chains, such as Japan. At divergent boundaries, tectonic plates move away from each other. In the oceans, magma from deep in the mantle rises to fill the gap. This creates underwater mountains and volcanoes along the seam. This process renews the ocean floor and slowly widens the ocean basins. By the way, a single mid-ocean ridge system connects all the world's oceans, making it the longest mountain range on Earth. On land, when plates pull apart, they form giant valleys, such as the Great Rift Valley in Africa. If this stretching continues over millions of years, East Africa could split off to become a new landmass. One famous example of transform boundaries is the San Andreas Fault in California. Unlike convergent or divergent boundaries, transform boundaries usually don't create mountains or oceans, but the grinding motion can cause powerful earthquakes, such as the 1906 earthquake that destroyed much of San Francisco. The floor is lava! Haha, just kidding. But honestly, it's kind of falling apart. You might not feel it yet, but a huge part of North America has already lost 37 miles worth of rock from its foundation. And no, this isn't about earthquakes or giant sinkholes. It's about the continent losing pieces of the very thing that keeps the ground from wobbling around like a bad carnival ride. A team of researchers has just dropped a geological bombshell. Part of North America's ground is thinning out like a very sad, very slow ice cream drip. How do they know? They basically gave Earth a high-tech full-body MRI and created 3D maps showing how rocks once considered indestructible are now melting away into the planet's guts, like an upside-down cheese pizza inside an oven. But to really understand this mess, you first have to meet my old friends, cratons. Cratons are like the roots of the continents. They're thick, tough, and ancient. We're talking billions of years old. These bad boys survived meteor impacts, supervolcanoes, and even the tectonic movement of plates. If the plates got into fistfights, for example, you can bet we would see mountain ranges being born. If they got a divorce, drifting apart from each other, then a whole new ocean would be born. All of these things leave scars on the surface of Earth, but the cratons seem to always remain unfazed, like the cockroaches of geology. And since a craton can basically get punched in the face and feel nothing, scientists always assumed these things were nearly indestructible. But then, a group of researchers took their fancy machines to the test and realized that, wait, the cratons are falling apart? How? Enter the Farallon Plate, a really ancient tectonic plate that started to slide under North America's major plate over 100 million years ago. This is a pretty normal process, actually. It's called subduction, and it's how Earth recycles rocks and keeps itself from overheating. This subduction thing has been happening for so long that, by now, the Farallon is almost 400 miles away from the craton, sitting pretty chill at the lower mantle, weirdly close to the outer core of our planet. But the Farallon has been causing trouble, like that one roommate who moved out but keeps leaving weird stuff in the fridge. You see, as it sinks, it tugs on the bottom of North America's foundation, stretching it out and causing pieces to fall off into the deep mantle. And if that wasn't enough drama, the sinking Farallon has also leaked water and carbon dioxide into the surrounding rocks, making the craton even softer and easier to shred apart. Thanks, Farallon. Very cool of you. By studying hundreds of earthquakes across thousands of monitoring stations, scientists have confirmed the story. Big chunks of continental material are dripping downward, thinning the craton by as much as 37 miles. That's more missing rocks than can fit into a milk carton. Sounds dramatic, right? But don't worry. This is happening at a snail's pace. It'll take millions of years for anything noticeable to happen. Your great-great-great-great few grandkids from the distant future might still be standing on solid ground. But don't get too comfy. This thing may not be an urgent problem, but there's another type of sinking that's happening faster than you can say, "Help!" Here's the thing. By 2050, at least 32 major cities in the US, including New York, Baltimore, and Charleston, could be partially underwater. And guess what? This one is mostly our fault. Scientists noticed that since 2007, some cities have been sinking into the ground between 0.04 and 0.08 inches every year. Charleston, in South Carolina, is pulling ahead in the worst way possible, sinking 0.15 inches annually. Sure, these numbers sound tiny and a bit ridiculous, but Charleston is barely 9 feet above sea level. And a little sinking goes a long way when the ocean is breathing down your neck. On really bad flood days, people there have to abandon their cars and basically swim home. This whole phenomenon is called land subsidence. And when you mix sinking land with rising sea levels, you get a disaster cocktail of flooded streets, salty farmland, ghost forests, and a lot of very cranky homeowners. And it doesn't stop with just homes. Infrastructure like bridges, roads, airports, and power plants, all things we rely on daily, are also at risk of serious damage. Flooded electrical grids and sunken highways could cause billions more in economic losses and create major safety hazards for communities. Now, let's be fair. Not everything is humanity's fault. Some of this trouble dates all the way back to the Ice Age. About 12,000 years ago, massive ice sheets covered the northern US. They were heavy, like seriously heavy. The weight pushed the land down, and when the ice melted, the ground didn't just pop back up like a trampoline. Instead, it started playing a weird game of geological seesaw. The places that were squished started rising, and the places that weren't got pulled down. This whole process, called glacial isostatic adjustment, try to say that 3 times fast. But of course, humans found a way to make it worse. Groundwater extraction is a major culprit. Think of it like pulling the stuff out of the mattress. After a while, the whole thing just sags. In places like California's Central Valley, the land is dropping by up to 8 inches a year because we keep pumping out water during droughts. In cities like New York, the problem isn't just water. Skyscrapers themselves are making it worse. Yep, turns out if you stack millions of tons of concrete and steel onto soft ground, it tends to flatten. And in case you're wondering, the total mass of New York City's buildings is around 1.68 trillion pounds. That's about the same as 3.5 million statues of liberty piled up. With so much weight concentrated over a relatively small area, the underlying soils have no choice but to compress over time. And if you thought it couldn't get messier, think again. We've been building dams, which stop rivers from delivering fresh sediment to coastal areas. That sediment is kind of like Mother Nature's way of fluffing the ground back up. Without it, coastal lands are compacting like an old sponge. Plus, when wetlands are drained for agriculture or construction, the peaty soil dries out and collapses. Honestly, it's like the ground just can't catch a break. Scientists also noticed that the areas that used to be lush wetlands are now among the fastest sinking spots in the country, especially along the Gulf Coast. Louisiana, for example, is losing about a football field of land because of this mix of subsidence and rising seas. So what's the end game here for us regular people who just want to live above sea level? Well, it's not looking great. Ghost forests, which are basically drowned woodlands, are popping up. Farmland is turning salty and unusable. And even sunny day flooding, where streets flood without any rain, is becoming a thing. Yikes! Meanwhile, over on the West Coast, California is not exactly winning either. San Francisco and Los Angeles are both sinking, which means that rising sea levels could hit them twice as hard and twice as fast. In some places like the Palos Verdes Peninsula, the ground has been sinking so fast, people over there might as well live like moles. So, is America turning into the next Atlantis? Probably not next week, but without serious action, like cutting back on groundwater pumping and planning smarter cities, at least 500,000 people are in serious danger. And the housing damage could easily rack up a jaw-dropping $109 billion by 2050. In the end, while North America isn't about to sink like a poorly made souffle, it's definitely showing some cracks in the crust. So maybe let's ease up on groundwater pumping, rethink how and where we build, and invest a little more in keeping our feet dry. After all, if the floor really does become lava someday, we're gonna wish we had at least fixed the leaks first.
It was April 2025 when geologists went back to Yellowstone's Norris Geyser Basin for the first time this year. And while doing their usual check, they realized that something was different this time. Where there used to be just a boring patch of ground, now there was a giant hole, about 13 feet wide, filled with weird, milky, light blue water. Everyone was terrified. Was it the sign that the Yellowstone supervolcano was ready to erupt? If so, it would be a worldwide disaster, the kind that destroys cities. According to the U.S. Geological Survey, if such an eruption occurred, the after effects would be felt all over the world. To start, the areas immediately surrounding Yellowstone would experience pyroclastic flows. That's the lava that erupts out of a volcano, including a high-density mix of volcanic gas, ash, pumice, and hot lava blocks. Those flows would destroy everything they touch, and an eruption of Yellowstone would send them into Wyoming, Idaho, and Montana. Areas further away from Yellowstone would escape the flows, but they would experience falling ash. It would come down heavily in the states closest to the epicenter. The ash would be especially dangerous for anyone breathing it in. The weight of the ash would also pose a serious threat. It would smother crops and collapse buildings as it piles up. Tragic consequences would be countless, but we'll talk about them later, because soon after the discovery, the weird pit surprised even experts. Geologists found rocks scattered everywhere. Some were about a foot across, and all of them were dusted with gray mud. This mud matched the walls of the new spring. It was like the place had simply exploded, but nobody had actually seen it happen. The team checked old satellite images to figure out when it appeared. In December 2024, the ground was totally normal. By January 6, 2025, a little dip had formed. And by February 13th, that water-filled hole was finally there. But the weird thing was that the sensors that usually pick up major hydrothermal explosions didn't detect anything. There was no giant blast or warning signs. Later, it turned out that this puzzling opening in the ground hadn't just popped up in one huge explosion. Instead, it formed from a bunch of smaller bursts over time. Little explosions first threw out rocks, then mud, and eventually created the pit. With time, it filled with silica-rich water. That was a huge relief for everyone. Yellowstone sits on a supervolcano, and its big explosions are a nightmare scenario. Luckily, this time, it was just a slow-building, small-scale explosion. It was dramatic, sure, but totally manageable. You see, Yellowstone National Park is full of geysers, hot springs, and all kinds of natural landscapes. But under the surface, things get incredibly intense, all because of the supervolcano. Now, supervolcanoes are often extremely large. They often have no cone at all, since they're typically the remains of gigantic magma chambers. Once, those chambers flared up, leaving behind a caldera. They're usually located over hotspots. It's no surprise that supervolcanoes can produce super eruptions, and when they do it, they blow more than 240 cubic miles of ash, molten rock, and hot gases up into the air. In other words, 4 super eruptions could fill the Grand Canyon to the brim. Supervolcanoes form when huge volumes of scorching hot magma escape from deep underground. This magma rises close to the surface but can't break through Earth's crust. So, a pressurized pool of bubbling magma gathers at a depth of only several miles. The pressure keeps growing because more and more magma is trying to get to the surface. And then, bang, a super eruption occurs. Now, back in 2015, researchers at the University of Utah mapped out the main magma chamber of the Yellowstone supervolcano and were shocked by its size. And then, they found another one below it. Together, these underground magma pools could hold enough molten rock to fill the Grand Canyon 11 times. All that magma pushes up on the ground above, which is why Yellowstone rises about an inch or two every year. That slow lift might not sound like much, but combine it with the fact that Yellowstone is still an active volcano and has a volcanic explosivity index of 8, and it's enough to make you wonder what could happen if things went south. And yes, Yellowstone has indeed been a bit jumpy in recent years. In March 2023, there were 354 earthquakes in the area. Most were tiny, but the biggest hit a magnitude 3.7, part of a swarm of 106 quakes. Now, before you freak out, experts from the Yellowstone Volcano Observatory say there's no need to panic. No eruption is coming anytime soon. Volcanoes don't stick to a schedule. Just because Yellowstone hasn't erupted in a long time doesn't mean it's about to blow. The park is stable for now, but scientists are keeping a close eye on everything underground, the quakes, the rising ground, and even temperature changes, just to be safe. The superhot plume of magma, a hotspot under Yellowstone, has been churning for 17 million years. The Earth's crust slowly moved over it, making the hotspot leave a trail of volcanoes stretching more than 450 miles along the Snake River Plain. Most of those ancient ones are now buried under layers of lava and sediment. In just the past 2.1 million years, Yellowstone has unleashed 3 cataclysmic eruptions, so massive they managed to reshape the land. Each explosion sent pyroclastic flows, rivers of searing hot rock, ash, and pumice racing outward for miles. The debris piled up in layers hundreds of feet thick, some forming solid lava-like rock. When those eruptions emptied the underground magma chambers, the roof collapsed, forming the massive calderas we see today. Even after those mega eruptions, Yellowstone didn't stop. Between 180,000 and 70,000 years ago, enormous rhyolite lava flows, sometimes over 144 cubic miles, poured out. Some flows followed north-south vent lines. The West Yellowstone flow erupted around 110,000 years ago. The Nez Perez Creek flow followed 160,000 years ago. If you stand at Madison Junction on the caldera's northwest rim, you can see it, a cliff that formed when the Lava Creek Tuff eruption collapsed the land 640,000 years ago. And inside the caldera, you'll see the hardened lava flows snaking across the floor. Figuring out when a supervolcano might blow is like being able to read nature's warning signals. Thousands of years before a massive eruption, the heat underground starts building, and the magma chambers become like ticking pressure cookers. Little signs start showing up. Gas bubbles escape as the pressure shifts, and earthquakes shake the ground. The land above slowly rises. Cracks appear. Hot springs and geysers start acting up, heating even more than usual. Now, what would happen if Yellowstone erupted? Remember those pyroclastic flows we talked about before? They can contain 2 parts: the lower flow of the hot lava that moves at ground level, and a cloud of ash that follows above the lava level. So the 2 of them would devastate huge areas. The ash would even reach Europe within 3 to 4 days of the eruption, but it wouldn't be so bad there. After that, it would only take around 2 to 3 weeks before cooler temperatures set in around the globe, all thanks to the sulfur gas that would get to the upper atmosphere after the eruption. Scientists predict that global temperatures would drop by up to 10 to 12 degrees. These consequences could last for 6 to 10 years, putting an end to monsoons, which could cause widespread famine in Asia. Scared? Well, don't be. The good news is that scientists don't believe that the sleeping giant under Yellowstone National Park will wake up in our lifetime. Experts say the next Yellowstone eruption won't likely happen for hundreds of thousands of years. And even then, it may not be that bad, because scientists have discovered that the magma lurking within Yellowstone is actually split up amongst 4 different chambers. Not only that, but some of the reservoirs of magma are likely to cool down and solidify, lessening the chances of an eruption. So, while an eruption does sound like it would change the landscape of the world, it's very unlikely to happen anytime soon. We all know that space missions come with a hefty price tag. To break it down, a ticket to space for an astronaut starts at around $20 million and can soar up to $50 million. NASA may be a well-funded organization, but you can bet they're always on the lookout to cut costs and save millions wherever they can. Plus, NASA has long realized they do not need to go to Saturn's moon to study if there's life there. We already have the suitable conditions for extraterrestrial life in Wyoming. If that resonates with you, then you already understand why NASA is so interested in Yellowstone. To explore life beyond Earth, we need to study environments that mimic extraterrestrial conditions. That's where all those hot springs come into play. Now, it's not the entire park that piques NASA's interest. Let's leave the bears, moose, and other Earthlings to our local biologists. The real hotspot is the geysers, where microbial life flourishes. Oh, by the way, Yellowstone has more geysers and hot springs than the rest of the world combined. In some of them, water can reach temperatures as high as 192 degrees Fahrenheit. You might think, hey, that's only good for steeping tea. But here's the thing. Life in the form of microbes not only survives but thrives in these extreme conditions, having adapted specifically to them. So, could these microbes help us find life on other planets? Absolutely. Now, let's shine the spotlight on the real superstar, the Grand Prismatic Spring. It's packed with silica, which gives it that stunning color. Silica reflects sunlight, especially the blue wavelengths, which is why it looks so vibrant. The coolest part, though, is not the color, but the fact that this spring can teach us a lot about how life evolved. Way back around 4.5 billion years ago, I wasn't around then, living things didn't know how to harness energy from sunlight yet, so they were using chemical processes instead, just like they do now at the Grand Prismatic Spring. But why are we talking about other planets? Well, if life on Earth kicked off in a comparable way to what we see in Yellowstone, there's a good chance we could find something similar elsewhere in the universe. And if we could nail down exactly how life started here, we could really fine-tune our search for life on other planets. Geysers, very similar to those in Yellowstone, can be found on moons like Enceladus, which orbits Saturn, and Triton, which is a moon of Neptune. But how do they compare to the geysers we see in Yellowstone? Well, back in 1989, NASA's Voyager 2 spacecraft made a groundbreaking discovery when it spotted geysers on Triton. This was the first time anyone had seen a geyser outside of Earth, not counting the volcanic eruptions on Jupiter's moon, Io, that were found by Voyager 1 in 1979. Since then, more geysers have been found on other moons in our solar system. In Yellowstone, geysers are heated by hot water from deep within the Earth. However, geysers on some of the outer moons get their heat from tidal forces, the gravitational pull from the big planets they orbit. You know how ocean tides on Earth are affected by the moon and the sun? Well, these moons experience something similar, but on a much larger scale. Beneath the icy surfaces of these moons are warm, salty oceans that stay liquid because the thick ice above keeps them insulated. As the moons move closer and further from their parent planets, the constant tugging creates heat, causing the warm water below to shoot out into space whenever there's a crack in the ice. This icy crust and the warm water underneath are a bit like a frozen pond on Earth. But could there be life swimming around in these hidden oceans, just like there are critters thriving beneath the ice of a pond? That's something scientists want to find out. NASA hopes to send advanced spacecraft to explore these distant moons and look for signs of life. But those warm oceans are buried miles beneath the frozen surface. So, how do we reach them? The answer may lie in geysers. In February 2019, a group of planetary scientists decided to visit Yellowstone in the winter to study the similarities between Earth's geysers and those in space. They know that Yellowstone's geysers are home to some tough little microbes called extremophiles, which thrive in extreme conditions like hot or acidic water. The researchers wanted to learn as much as they could about these microbes and the environments they live in. They brought along a bunch of scientific tools to measure things like temperature, pH levels, and oxygen in the water. They also used special instruments to analyze the chemicals in the ice and rocks and sniff the air for gases. Plus, they collected samples of rock, ice, and water from the geysers, catching tiny droplets on sheets of foil coated in geyser spray. Their main target was the Great Fountain Geyser in Yellowstone's Midway Geyser Basin, which puts on a spectacular show 2 to 3 times a day. However, visiting in winter posed some challenges. Some scientists were delayed by snowy weather, arriving late at night right before they were supposed to enter the park. Then their SUV got stuck in a snowdrift and had to be rescued by a snowplow. The next day, riding in a snow coach, the team had to trudge through deep snow for nearly a mile to reach the geyser, keeping an eye out for elk, bison, and even bears. As they made their way to the Great Fountain Geyser, they took breaks to gather samples and measurements from other interesting pools along the way, like Lemon Pool and Surprise Pool. Even though Yellowstone feels remote, it's not nearly as far away as places like Enceladus and Triton. It's a unique natural laboratory that can teach us a lot about life on Earth and potentially beyond. Oh, as for labs, the Great Prismatic Spring may count as one. Look at these guys. Under the microscope, they look like matches. Their official Latin name is Thermus aquaticus. They live in this hot spring, and these bacteria have saved millions of people's lives. Now, if you're skeptical about what I just said, then you need to know that these bacteria help to create the basis of PCR tests widely used in today's medicine to give fast and precise diagnosis. Back in the 60s, a microbiologist named Thomas Brock was exploring the park's superheated thermal pools and stumbled upon something amazing. Brock was super interested in bacteria that could thrive in extreme conditions. During his 10-year journey studying geysers and thermal springs, he found a microbe in a spring called mushroom pool that could survive in nearly boiling water. This little guy, Thermus aquaticus, turned out to be a game changer for science. Why? Well, it's crucial for a technique called PCR, also known as polymerase chain reaction, which is used to quickly make copies of DNA samples. Before Brock's discovery, this process was tricky because the heat could damage the enzymes that hold DNA together. But thanks to Thermus aquaticus, scientists could now heat and cool DNA samples without breaking them down, making everything faster and easier. It all happened because researchers had purified an enzyme called tag polymerase out of this organism. Those Yellowstone microbes could also be your new go-to for a delicious and sustainable breakfast. A unique microbe was discovered there during some NASA-funded research, and it's now being transformed into tasty vegan breakfast patties and cream cheese. Originally found in a hot spring, this little wonder is called Fusarium strange flavolapsus, and it caught the attention of space enthusiasts as a powerful protein source for long space missions. Plus, it requires way less water and land than beef, making it a smart choice for the planet. Researchers initially looked at this microbe for biofuel, but soon realized it could be cultivated into a complete protein with a texture reminiscent of chicken. Marked as FY, it can be turned into a variety of food products, all thanks to a fermentation process that keeps it free from contaminants. Oh, almost forgot. NASA is even working on a bioreactor to grow FY in space. Ooh, stay tuned.
About 2 billion years ago, a massive asteroid crashed into Earth, leaving behind total destruction and what we now call the Vredefort crater in South Africa. And get this space invader might have been way bigger than scientists originally thought, possibly twice the size of the asteroid that wiped out the dinosaurs. Nowadays, the Vredefort crater is about 99 miles across, which makes it the biggest visible crater on Earth. But technically, it's still smaller than the Chicxulub crater in Mexico. The latter is about 112 miles, and it was left by the infamous dinosaur distractor 66 million years ago. But the thing is, craters don't stay the same forever. Over time, erosion wears them down. That's why they start looking smaller than they used to. And scientists think that when the Vredefort crater first formed, it could actually reach 174 miles across. That means it was the biggest impact site Earth has ever seen, even though it looks smaller today. Just imagine how insane that impact must have been. A space rock that would have sent shockwaves ripping across the planet, triggered enormous wildfires, and completely changed the climate. The asteroid likely hit Earth at a very, very high speed. But since this catastrophe happened billions of years ago, way before dinosaurs or even complex life saw the light of day, it didn't wipe anything out like the Chicxulub asteroid did. At the same time, recently, researchers have realized that the asteroid might have been even bigger than they thought previously, up to 15.5 miles wide. As for the speed at which it slammed into Earth, it could reach a staggering 56,000 miles per hour. Now, figuring out how big Vredefort originally was, that's been a bit of a headache. The main issue is that it's super old, and we're talking about 2 billion years old. No wonder that over that much time, erosion has kind of worn it down. So it's hard to tell just how huge it once was. But it's not just erosion causing the problem. Over the years, new layers of rock have built up over parts of the crater, and they've covered up most of the original structure. That's why now only little pieces of the raised rim are left, and this makes it even harder to get a clear idea of how big it was. So, scientists started looking at the minerals around the crater, like quartz and zircon. They discovered that those were all messed up by the asteroid's impact. They had tiny fractures caused by the blast. Researchers studied those damaged crystals and managed to figure out how far the explosion actually spread. Equipped by this new knowledge, scientists now believe that their latest estimates of the size of the asteroid are the most accurate ones. The reason why we haven't heard much about this disastrous impact is that, unlike the Chicxulub asteroid, which wiped out the dinosaurs and reshaped life on Earth, the Vredefort asteroid hit at a time when Earth was a very different place. There were no trees, no animals, just single-celled life in the oceans. That means no mass extinction, no burning forests, no fossilized evidence of chaos. But scientists think it still had a massive impact on the planet. It might have changed the climate even more dramatically than the asteroid that ended dinosaurs. But since we don't have much direct evidence of the disaster, studying what's left of the Vredefort crater is one of the only ways to understand just how powerful this impact was. Even though it happened billions of years ago, learning about this impact can help us understand the history of our planet, and maybe even prepare for future asteroid threats. After all, they could be similar to what happened in Siberia at the beginning of the 20th century, pretty recently. It was a warm morning, June 30th, 1908, when the sky suddenly lit up with a blinding flash. What followed was an explosion so powerful that it remained a mystery for decades. Known as the Tunguska event, it was one of the most baffling disasters in history. Scientists suspected an asteroid impact, similar to the one that wiped out the dinosaurs. But there was one eerie problem. No crater was ever found. The explosion struck deep in the remote forests of Siberia, near the Podkemenaya Tunguska River. The blast was beyond anything seen before, flattening around 80 million trees across an area of 830 square miles. The sheer force of the event was mind-boggling. It was strong enough to devastate the landscape, scorch the ground, and wipe out countless animals. According to witnesses, there was an eerie glow in the sky, which was followed by a streaking fireball with an intense bluish light. It was brighter than the sun. Moments later, there was a deafening blast. The shockwave was so powerful that it shattered windows hundreds of miles away, and people were knocked off their feet. Yet, despite the destruction, the source of the explosion left no obvious trace. Later, scientists finally started to understand what had occurred on that day. Imagine a meteoroid racing into Earth's atmosphere, transforming into a blazing meteor. It's traveling so fast that the air in front of it compresses and heats up, setting it on fire. But it's so large that it doesn't just burn up all of a sudden, it explodes. When that happens, the blast releases so much energy that a powerful shockwave spreads out. And since the explosion happens in the air, it leaves no impact crater. Back in the early 1900s, with limited technology and the remote location, scientists were left with a puzzle. Only much later did they eventually conclude it had been an airburst, where an object explodes high in the atmosphere, never striking the ground but releasing enough energy to devastate the area. Most likely, it was a giant asteroid about the size of a 25-story building. It could have been moving at around 33,500 miles per hour and exploding about 3 to 6 miles above Earth's surface. Another wild story happened back in the late 90s, but it wasn't Earth that was affected. A comet got stuck in orbit around Jupiter. One day, it got too close, and Jupiter's immense gravity broke it apart, turning it into a bunch of pieces. Some of them were as big as half a mile across. Scientists were curious because they didn't know what would happen when those pieces hit the planet. And in July 1994, the moment came. The comet's broken up pieces started crashing into Jupiter, one after the other. Over 6 days, 21 chunks of the comet smashed into the planet at insane speeds, like 37 miles per second. That's more than 130,000 miles per hour. The impacts were so powerful that they heated up Jupiter's atmosphere to a mind-boggling 53,000 degrees Fahrenheit, which is way hotter than the sun's surface. When each chunk hit, it sent massive plumes of material flying out of Jupiter, like when you throw a rock into a pond, but way bigger. Some of these plumes shot up almost 1,900 miles into the sky. Afterward, big dark scars appeared in Jupiter's atmosphere, and they stayed visible for months as the debris spread out across the planet. But this wasn't just a cool space event. Scientists actually learned a lot from it. Those dark impact marks helped scientists track the winds in Jupiter's stratosphere. The crashes even caused temporary changes in Jupiter's glowing auroras, showing that the planet's magnetic field was affected by particles from the explosions. Plus, the comet fragments didn't just make a mess, they also left behind new chemicals in Jupiter's atmosphere. Plus, some chemicals were also exhumed from the lower atmosphere. Some molecules like ammonia broke down over time, but others, like hydrogen cyanide and water, are still floating around Jupiter today. This helped scientists understand how different chemicals react and mix in Jupiter's atmosphere. Comet Shoemaker-Levy 9 was a wake-up call. It proved that massive space collisions still happen in our solar system. That's one big reason why NASA started looking into how we can track and prepare for any future impacts that might threaten Earth. Whether it's learning more about asteroids and comets, or about how giant impacts shape planets, the importance of such discoveries is undeniable.
Oh look, there's a giant blob heading straight for New York City. Oh wait, hold on. You'll actually have to look down, not up. Because this blob is a mass of hot rock moving beneath the Earth's surface. And when it finally reaches the Big Apple, some say it could tear the continent in two. But Yankees fans, and even you Mets fans, don't worry, this journey is going to take about 15 million years or so. You see, a long time ago, people noticed something curious. When they looked at world maps, they thought, don't the continents look like puzzle pieces that could fit together? That couldn't just be a coincidence, right? Then, in the year 1912, a German meteorologist named Alfred Wegener came up with a revolutionary idea, something we now know as the theory of continental drift. Wegener said the continents are always on the move, and those huge chunks of land we see today were all once connected, forming one giant supercontinent called Pangaea. That idea suddenly explained a lot of mysteries, like why fossils from the same species turn up in different corners of the world, even though entire oceans lie between them, or why coastlines of continents match up so neatly, just like South America and Africa. Wegener also explained that mountains form when a drifting continent runs into another one, crumpling the land and pushing it upward. That is exactly how the Himalayas came to be. The Indian plate collided with the Eurasian plate, and the land rose into the massive mountain range we see today. Now these days, everybody learns about Wegener's idea in school and takes it as fact. But back then, many people thought he was completely out of his mind. I mean, whole continents moving around? What on earth could push them? That's why it took scientists more than 50 years to finally go, oh, I see, it's the Earth's mantle. Yep, slow-moving currents of hot rock deep in the Earth's mantle push the tectonic plates around, and that means the continents move too. Picture super tough puzzle pieces floating on top of boiling oatmeal. That's a picture. Yep, they drift, and sooner or later they crash into each other. This is what happens on Earth's surface. And that's how we finally agreed that Wegener was right. But what if I told you that might not always be the case? Some experts agree that the supercontinent Pangaea started breaking apart about 200 million years ago. And that's how we ended up with the world map we know today. But a recent study is challenging part of that idea. And it all comes down to a giant mass of hot rock, something scientists call the Northern Appalachian Anomaly, or just NAA. Yep, what we casually call a blob, the experts call an anomaly, and that is simply because it is hotter than the rock around it. So, this anomaly sits about 124 miles beneath the mountains of New England and stretches up to 249 miles wide. It lies in the asthenosphere, the semi-molten layer of Earth's upper mantle. But here's the strange part. It should not even be there. I mean, rock formations like this normally don't exist in that part of Earth's interior. For years, scientists thought the anomaly was left over from when the North American continent broke apart from Northwest Africa about 180 million years ago. This new study says that might not be the case. It suggests the blob is actually linked to the process that split Greenland from North America only about 80 million years ago. The idea then is that this blob is a leftover from when the landmass broke apart, a piece that never quite settled down. This is one stubborn blob we're talking about because it is still on the move, super slowly. But still, it moves only about 12 miles in a million years. Over time, it's already traveled more than 1,100 miles from where it first appeared. And now, New Yorkers, watch out! This blob of scorching hot rock is heading your way. Okay, I know, I'm being a little dramatic. The truth is, we really don't have to worry. First, scientists say it won't even get near the city for at least 15 million years. And second, even though we call it a blob, it is not something gelatinous. It is not oozing. And it is definitely not going to push its way up through the Earth's crust and invade the New York subway, or anything like that. That is just not going to happen. What the anomaly will look like, or what it might do to the continent in the future, is still a mystery for geologists. But they are pretty confident it will not have any real impact on human infrastructure or on our daily lives. It is not like lava that's suddenly going to burst through the floor of your house. That's because, at the end of the day, the blob is just rock. Like any rock you see on the street, only super high, enormous, and buried deep inside the Earth. To explain why this rock is sitting in such a weird spot, scientists came up with what they call the mantle wave theory. So think of it kind of like a lava lamp. After continents break apart, hot, heavy rock can detach from the bottom of the tectonic plates in blobs. These blobs, or pieces of rock, move around under the crust and create waves. When that hot material slips under a continent, it works like the flame under a hot air balloon. It gives the land a little lift. Then, when continents stretch and split, space opens up underneath and semi-molten rock quickly fills in. Eventually, it cools down, gets heavier, and sinks. Meanwhile, hotter mantle material rises up and creates a warm patch called a thermal anomaly. This sudden motion shakes up the base of the continent. Imagine a row of dominoes. One piece falls and the rest follows. Blobs of rock start dripping downward one after another, and over time, they slowly move inland. Scientists think these rock currents keep flowing, rippling under the surface for millions of years. Now, knowing all this matters because the anomaly might have played a role in shaping the land above it. For example, it may have lifted up some ancient mountains over the past few million years. That helps to explain a big mystery of the region, why the Appalachians are still standing. I mean, why haven't they worn down as much as you would expect after all this time? Well, think about it. The Appalachians are ancient. This mountain range in North America started forming hundreds of millions of years ago, long before the dinosaurs. With all that time, rain, wind, and erosion should have worn them down to almost nothing by now. Honestly, some geologists expected them to be rolling hills at best. But nope, they're still mountains, pretty ones too, and much bigger than they should be. And here's where the blob comes in. See, when a giant pocket of superhot rock sits under a mountain range, it can actually give the crust a little lift. It's kind of like putting a balloon under a blanket. The blanket rises up. The heat makes the Earth's crust lighter. So even while wind and rain are wearing the mountains down from above, the Earth is gently pushing them back up from below. There is another positive takeaway from this study. These new insights can help scientists better understand other strange geological features around the world. In fact, the researchers believe they may have already found a twin to this blob, sitting under north-central Greenland and also tied to the Labrador Sea. So, what can we conclude from all this? Well, tectonic plate movement is still the reasons continents break apart. But the process goes much deeper than we thought. The effects of ancient rifting can still play out millions of years after the surface split, just like what happened in Greenland. Although it's still really hard to predict what this anomaly will look like in the future, we know one thing for sure right now. There is nothing to fear, and I'm betting that most of us won't be around for that.
Imagine standing in a quiet northern town, surrounded by mountains and forests, when the ground beneath your feet suddenly shifts with the force of a freight train. That's not a movie scene. It's a very real possibility for the people living in Dawson City, Canada. Hidden beneath the tranquil Yukon landscape lies a geological giant, the Tintina Fault. For more than 12,000 years, it has been silent. But new research suggests it might be ready to wake up in a spectacular and dangerous way. Stretching over 1,000 kilometers from the Yukon into Alaska, the Tintina Fault is like a massive crack in Earth's crust, a boundary where colossal slabs of rock slowly grind past each other. On the surface, it looks harmless, just rugged terrain, rivers, and forests. But deep underground, strain is quietly building, like a spring being wound tighter and tighter. Theron Findlay, a geologist from the University of Victoria, and his team decided to take a closer look at a section of this fault near Dawson City. This wasn't just a casual inspection. They used cutting-edge tools like high-resolution satellite images, aerial surveys, and LiDAR, a laser-based scanning method that can reveal subtle changes in the ground's shape. What they found was unsettling. In one location, the ground was visibly displaced by an astonishing 1,000 meters, evidence of a long series of powerful earthquakes millions of years ago. In another area, they spotted a smaller but still significant offset of about 75 meters, likely caused by more recent quakes, roughly 132,000 years ago. Since then, nothing major. At least, nothing visible. And that's exactly the problem. When a fault line hasn't released energy for thousands of years, it doesn't mean it's safe. Quite the opposite. It could mean that massive pressure has been silently accumulating. Based on their calculations, the Tintina Fault has been moving at a slow creep of up to 0.8 millimeters per year. Over 12,000 years, that adds up to a staggering 6 meters of potential movement waiting to be unleashed. If that strain were to suddenly break free, the resulting earthquake could be bigger than magnitude 7.5. For context, that's in the same league as some of the most destructive quakes in history, like the 1976 Tangshan earthquake in China, or the 2010 Haiti disaster. While the Yukon isn't densely populated, the impact could still be devastating, damaging highways, collapsed buildings, landslides cutting off communities, and potentially loss of life. The scientists can't say when it will happen. Earthquakes don't work on a schedule, and predicting the exact moment of rupture is one of geology's greatest challenges. What they do know is that the Tintina Fault is in what's called a late stage of its seismic cycle, a point where the risk of a major quake is higher. For the people of Dawson City and surrounding areas, this means living with a quiet but ever-present threat. Emergency planners might advise residents to have evacuation routes, survival kits, and backup communication plans. But in the end, this is a reminder of a simple truth. Earth is never truly still. Even in the most peaceful landscapes, immense forces are always at work, reshaping the planet in ways we can't always see, until the day they reveal themselves with a violent jolt. Yet, the story of the Tintina Fault is more than a warning. It's a glimpse into how Earth stores and releases its pent-up energy. Each millimeter of annual movement is like another twist of a key in a lock. At some point, the lock will turn, and when it does, the release will be sudden and powerful. LiDAR images reveal ancient scars across the land, subtle to the untrained eye, but obvious to scientists. These are the footprints of past disasters, frozen in the ground like a history book carved by nature. Finley and his colleagues believe the region's seismic silence has lulled people into a false sense of security. A place can be both beautiful and dangerous, and the Yukon is a perfect example. Visitors come for the sweeping vistas and endless wilderness, rarely realizing that deep beneath their hiking trails and scenic roads, forces are shifting that could change the landscape overnight. This hidden drama plays out all over the world. Fault lines in California, Turkey, Japan, and beyond all share one trait. They eventually break. The question is never if, but when. The Tintina Fault just happens to be one of the quieter players, which in geological terms can be far more ominous than the noisy ones. And so, the clock ticks, silently, in the frozen north, counting down to a moment no one can see coming. On January 26, 1700, one of the biggest earthquakes in history hit off the coast of the United States. It had a magnitude of 9, which puts it in the top 10 most powerful earthquakes ever recorded. This earthquake triggered a huge tsunami and changed the coastline all the way from southern British Columbia down to northern California forever. Back then, the area wasn't very populated, but thanks to some clever research, scientists figured out exactly what happened that day by looking at old geological records, tree rings, and even some history from Japan. On the same day as the earthquake, a massive tsunami also hit Japan's eastern coast. For a long time, no one connected the two, but in the 1980s and 90s, researchers realized the tsunami in Japan had been caused by the earthquake in the Pacific Northwest. They were also able to pinpoint the exact day, January 26, 1700. They even found old trees in coastal Washington that had all perished around the winter of 1700, which matched up perfectly with the timing of the earthquake. The earthquake came from the Cascadia subduction zone, a fault where the Juan de Fuca plate slides under the North American plate. This fault stretches about 700 miles, from northern Vancouver Island in British Columbia to Cape Mendocino in California. The pressure from the moving plates builds up over time, and eventually, another big, devastating earthquake will hit the same region. It's just a matter of time. By looking at the geological records, past tsunami deposits, and signs of land level changes, scientists can figure out how often these huge earthquakes happen. Emergency planners have been preparing for the next big quake, often calling it the big one. Scientists believe earthquakes in the Cascadia subduction zone happen every 200 to 1,000 years. And since the last major one was over 300 years ago, the Pacific Northwest is definitely due for another. When it happens, the earthquake is expected to be as big as the one from 1700. But this time, it'll affect around 15 million people. The devastation will be severe. Buildings will collapse, roads and runways will crack, and bridges will fall. Communication in and out of the area will be cut off. But the worst part? The earthquake will trigger a massive tsunami that might hit parts of the Washington coast in as little as 10 minutes. It's not a matter of if, but when the Cascadia subduction zone will break. When it happens, it will be the worst disaster the US has ever faced. Worse than the Hurricane Katrina or Superstorm Sandy. It'll impact an enormous area, stretching from southern British Columbia all the way down through Oregon to northern California. That means millions and millions of people will be affected. Fairchild is considered a backup staging area for handling the aftermath of the earthquake, with Grant County International Airport in Moses Lake being the main one. For those who will survive the initial quake and tsunami, the aftermath could be just as disastrous. Aftershocks will follow, and transportation will be a mess. Roads will be damaged or completely blocked, airports will shut down, and most of the main routes, like Interstate 5, will have bridges destroyed. This means food and water supplies will be cut off, and it will be incredibly difficult for help to get in or for people to escape. Gas pipelines will most likely be damaged too, and restoring them could take anywhere from a few days inland to weeks or even months along the coast. Power outages will be widespread within 100 miles of the coast throughout the entire Pacific Northwest, and water could be out for 3 to 7 months. Even telecommunications will be down for 2 to 3 months across the Pacific Northwest, Alaska, and even parts of East Asia. The good news for eastern Washington is that it will mostly avoid the worst of it, thanks to natural barriers between the west and east sides of the state. The tsunami may hit the Columbia River Gorge, but it will lose energy quickly because of a sandbar under the river. The Cascade Mountains will absorb much of the earthquake's impact, so the east side won't feel it as strongly. And since eastern Washington won't get hit as hard, it'll be up to them to handle the aftermath of the quake. That means helping western Washington, taking in refugees from the areas that got destroyed, and delivering supplies to where they're needed. Scientists have looked at other major 8.0 to 9.0 magnitude earthquakes like the ones in Chile in 1960, Alaska in 1964, and Sumatra in 2004, and Japan in 2011. These kinds of quakes can shake the ground for anywhere between 6 to 10 minutes, and that's a long time for the ground to be shaking. Such quakes are super intense because they happen close to Earth's surface, so it's not just a quick shake. It's a long, strong one that can cause a lot of damage. If the Cascadia earthquake and tsunami were to hit tomorrow, over 13,800 people could lose their lives, and about 107,000 people could be injured. The economic toll in Washington, Oregon, and California could top $70 billion. To put that into perspective, we can compare these numbers with some other major earthquakes. In Chile's 1960 earthquake, about 1,650 people lost their lives. The 1964 Alaska quake resulted in around 140 lives lost. The 2004 Sumatra earthquake and tsunami took the lives of an estimated 280,000 people. And the 2011 Japan earthquake and tsunami caused over 20,000 casualties. Authorities know about the dangers of the Cascadia fault, but even with all the planning, no one can say for sure what will be needed when the big quake hits. Right after the earthquake and tsunami, the areas outside the immediate disaster zone won't be able to help much because roads and airports will be destroyed, and resources will be limited. How can we deal with this kind of disaster and its effects? We don't have all the answers yet. Right now, let's focus on the Cascadia subduction zone. It's a huge fault line that stretches about 620 miles from Vancouver Island to Cape Mendocino in California, sitting about 93 miles off the coast. It's like one tectonic plate is slowly sliding under another. When the plates are close to the surface, about 18 miles deep or less, they get stuck because of friction, kind of like pushing two rocks together. Over time, this creates a lot of pressure. When the pressure finally becomes too much, the plates slip, causing a massive earthquake. This is called a megathrust earthquake, and it can be huge. Below the area where the plates are stuck, there's a zone where the plates move really slowly. We're talking about just a few inches every few months. This slow movement helps to release some of the pressure, but it also builds up more pressure on the parts of the fault that are still stuck. This means that over time, it increases the chances of a huge earthquake happening. These massive quakes, called Great Subduction Zone earthquakes, can be stronger than magnitude 8.5. Megathrust earthquakes are the biggest earthquakes that happen. They can go over a magnitude of 9.0, which is insanely powerful. Just to put it in perspective, a magnitude 9.0 earthquake releases 1,000 times more energy than a 7.0 and 1,000,000 times more energy than a 5.0. These earthquakes happen when a lot of pressure builds up in a part of the fault that's locked, which means the plate can't move past each other. When that pressure gets too high, the fault finally ruptures, releasing all that built-up energy in one massive shake. The Cascadia subduction zone is super long. That's why if it were to rupture all at once, it could produce a large earthquake. Scientists have studied this region and found that about 18 miles below the surface, the fault is completely locked. The plates there aren't sliding past each other. But deeper down, the plates start to slide more smoothly, causing less friction. This is important because it tells us how much stress is building up in that locked zone, and how it could eventually lead to a major earthquake.